special New Year's Eve Best of AI show. If your New Year's resolution is to learn more machine learning, then stay tuned for 3 segments we dug out of the AI show archives. Number 1, a talk I gave on Canada about the fundamentals of deep learning. Number 2, Jeremy Howard himself tells us how to make AI applications without a PhD. And finally, a talk I gave earlier this year talking about principles of MLOps. Enjoy. So basically, what I'm going to do is, this is an introduction to deep learning, but my sense is that all of you know a lot of stuff, so I will go fast or slow depending on what's going on, because I have put way too much stuff in here. Basically, I'm going to motivate convolutional neural networks from first principles, and then show you what it looks like in TensorFlow, because you probably all know what it looks like, and then show you how to run it on Azure, basically. Okay, and so obviously that sounds like a lot of stuff, because it is. And so I will go fast or slow depending on what you tell me to do. And so since Canadians are super nice, you can basically just be like, and I'll be like, okay, I'll or be like, and I'll know, okay, in your nice way. And you won't have to say sorry for it afterwards, okay? Just FYI. So the thing about machine learning and deep learning, and since you are all, I'm assuming, practitioners, and if you're a beginner, that's okay too. This is for everybody. The thing with machine learning is we have this kind of super huge gap of understanding to overcome, because terrible things have been done with AI and machine learning, right? Come on, that's funny, right? It's a Clippy. They're all looking at me. These are the jokes, people, okay? And the thing about it is that everyone today is all about machine learning or deep learning, right? And as you know, the difference between machine learning and deep learning depends on the marketing guy, effectively, right? And so that's the important thing. And the reality of the matter is, when I explain it to people, let's just say, because I'm assuming you all know this stuff, but this is how I explain it to people, so that if you ever need to, I always say, look, you know, when we're talking about AI, it means a lot of other things too. If you remember, like way back in the day when the Deep Blue chess thing beat Kasparov, that's AI. But it's not machine learning. And it's very important to distinguish, right? And the way I like to think about it is the search space. The size of the search space kind of helps you know where things are. Like the search space in chess, while large, is still finite. The search space in the amount of pictures that people generate is infinite. Because I have seen some crazy stuff on Twitter, right? And you know this. And then our parents put really crazy pictures on Facebook, right? So what is the difference between artificial intelligence and machine learning, right? In my professional opinion, artificial intelligence is a glorified search problem, right? You remember algorithms like A star, Minimax, they're all searching in trees with a good strategy. And this is how I like to think of AI, and I like to think of it as the hard part of AI, where there is a fixed problem space, right? When it comes to machine learning, there's a little bit of squishiness about the problem. And instead of searching a space, what we are doing instead is providing examples to generate an algorithm, right? And most people don't like this, because when I say algorithm, I mean model. We're building a machine learning model. But if you think about it, it's just a different way of making a function. It just looks weirder, right? And if you open like an HDF5 file in front of people that have never done machine learning, they think the machine's going to explode and glitter's going to come out, right? Because it's AI, but it's the file. And I say, well, it's basically a bag of numbers in a network. Sorry, right? Sorry to disappoint you, Steve, from marketing, right? It's not any more than that. It's a function that's written with data. So then what's the difference between machine learning and deep learning? Because some will tell you that neural networks belong in the space of machine learning, right? But then if you get to n number of layers, then it becomes deep learning. It is still an open question what that number n is. Again, it depends on the marketing people, in my opinion. Right, because you've seen ResNets. I think, how high do they go? They go pretty high now. ResNet. I'm a computer vision guy, and so I think in terms of computer vision. But these things can get pretty deep, and they do some pretty amazing stuff. And then the question that I always get from business people is, well, when should I use it? And that's an important question, right? Because everyone's like, hey, you should use AI. Just use AI, and you're like, I don't think you know what this is. We're making a function in a different way, right?
So the example that I like to give, and maybe this will be helpful to you when you talk to your management about what this can do, is the example of a check. Anyone work for a bank? Oh, did I just make the thing go away? The screen? You still good? You got my screen? Okay, good. So anyone work for a bank? Okay, there's always a couple of you. And the people that work for banks are like programmer saints, because the kind of data they deal with is just, it should be on the Dirty Jobs show, right? Right? It's like they're using COBOL, and for some reason, Bill always puts the name in the age field, and COBOL lets you do that, right? And that's what they have to deal with. So imagine you work for a bank, and you show up one day, and the guy comes down and is like, we have a really good idea. We want you to write an algorithm that detects whether the pictures of the check from the users are upside down or not. That's an easy problem, because your bank is cheap, and all of your bank checks have a black stripe at the top. Can you solve that? You can. And you all know that you just sample 100 random pixels at the top, and if they're all black, good. If they're not, you switch. So you tell Steve from marketing, I can do this, it's going to take 6 hours. It's really going to take 3, but it's a lot of YouTube to watch. Right? Someone has to watch all that stuff. If little Billy wants to talk about his life, we need to listen. So you do this, and one day, and he comes back the next day and says, I have a really even better idea, and it's just this one thing. And anytime a non-technical person tells a technical person it's just this one thing, we have to sit down. Like, no one will go up to a civil engineer and be like, hey, just this one thing turned the bridge upside down. But they will do that crap to us all the time, right? So he goes, just this one thing. The owner of the bank, Sally, loves her horses, and she wants a picture of her horse on the check. Just this one thing. Now, could you write an algorithm to solve that check upside down problem? You could. You would ask for the check. You would do the bunch of if statements, and you'd go home and take an extra long shower because you wrote that code. But it works. Now, imagine if you have to do this for any person, for any check, for any picture. Did you feel that gap as a programmer? You felt it, right? That's the gap where machine learning works. And that's how because programmers have this intuition about programming, and when you put that gap into their head, they're like, oh, I can't write that. No, you can't, but you can give the machine examples such that it can produce models for them, right? And that's how I explain that gap, because intuitively programmers will start to code in their head, black stripe at the top, horse has pixels over here, and I can fake that somehow, right? And I can do some transformations. But then when you say any picture, any check, any person, they can no longer do that, but they know that a computer must be able to somehow. And this is where we sort of say, there's where machine learning works. And that's how I explain it. Now, all of you know machine learning, and so I'm explaining it to you this way because you already know, but when I talk about it to people that don't know, I literally make programmers feel the pain in that gap, and that's where machine learning works. Because as you know, programming is we make a function, we give it some input and outcome answers. In machine learning, we swap that around. But we don't call it a function, we call it a model. We don't call it answers and input, we call it data in machine learning. Right, and this you all know, it's just a different way to think about it when you're explaining it to the programmers who don't appreciate the pain we go through every day. Like, if something works the first time, we're different. We know something's very wrong. Programmers are like, I'm a friggin' genius. And we're like, oh, something's terrible. How is this possible? But what goes in there? So again, what we're doing is we're making a function such that we can predict on the things that we're going to build, but it's not clear to some people what these things look like. To you it is, and so I'm going to go through an exercise to motivate from first principles how it works, and we're going to use images like this. Okay, they're very stupid. This is stupid, but we're going to build all the way up to convolutional neural networks from the bottom up, and if you want me to go faster, remember. Okay, so I am going to ask you to build a machine learning algorithm, and you wouldn't do this, that predicts whether these pictures are darker at the top or darker at the bottom. Okay? How would you do that as a regular programmer? By the way, this is what the data looks like. So for example, this one is darker at the top because there's the answer. This is darker at the bottom, and there's that first picture. How do you know this one's darker at the top? You can use your regular programmer lizard brain. And I used to teach high school, so awkward silence is only awkward for you. Every time it's like, well, that makes me feel awkward. Yeah, not me. Yes, what would you do? So the answer that he gave was add the top, add the bottom, and compare. Right? Easy. Some people were like, some other people who, because you all are smart, you would come up with this. Other people like take the average of the top and the average of the bottom, but as you know mathematically, it's two wasted divisions. Right? Easy. Now, what if I forced you, like to think of this intuition, add the top, add the bottom. What if I forced you to put it into something like this? Where I asked you to invent some magic W's such that when you multiplied all of the input values, you would get an answer that would say top or bottom. How would you do, what numbers would you put in for W's? Yes? 1, 1, 1 here, zeros, minus ones. That's super clever, right? Because it basically what it does is it adds the top, adds the bottom, negates one side, and then they fight. Because as I learned in 4th grade, and this has magically served me very well, there's no such thing as subtraction, only addition of negative numbers. Saved my life as a 3rd grader. I remember getting all the minuses and putting a plus and then a negative. I'm like, okay, I know how to do this. Right? And if you think about it, if it's more negative over here, right, than it is positive over here, the answer will be negative, we guess bottom. Otherwise, we guess top. Super easy. What if it's 0? They're the same. Flip a coin. Right? And that's okay. Any questions about this? See, and this is where I'm tricking you. Because there's something hanging out over there that you should have all seen. Right? This is supposed to be interactive. We're all friends here. Canadians are nice. What's the B? Great question. Well, what if we wanted to guess bottom, even though it's not darker than the top, but it's within a couple of shades? Like if it's dark enough, right? Then you add a negative number. Right? And what that does is it forces this to be more negative. But what if we want to do it to the top? Then we add a positive number, and all of a sudden, we're guessing a top. It's almost as if we're biasing our answer. And in machine learning, we're super clever. We call that the bias. Yeah, who knew? We're so clever. Right, this is simple, and you've all seen this, right, as a perceptron algorithm. It's the simplest thing, but it's basically a dot product of the two things. If it's negative, bottom, positive, we guess top. Now let's try it out, right? Clearly works. You can see bottom right, this number comes out to be 236, so we guess top. This number comes out to be minus 234, we guess bottom. Now, don't ever use machine learning for this problem. That's dumb. We wouldn't do that. So basically, and this is where everyone else in the universe except for you all gets surprised, I say that W you just invented is a machine learning model. Right? I know I'm trivializing our work, but it is. If you think about all the other machine learning models you build, it's just that, but more of them. What about top, middle, bottom? What if I wanted to guess? Well, you just make 3 of them. And now instead of a single vector, it becomes a matrix. Right? And we do what I like to call a cookie monster operator because I'm 5 years old. You take this thing, right? You turn it on its side and go num, num, num. Dot product 3 times gives you the answer. The one with the highest number is the one that's the darkest, right? And this is why me and Dave were talking earlier. That's why I hate when people say the output of models like this have a probability. Like, because we softmax over the end, and we're like, oh, this is it's not a probability. We're forcing everything to sum to 1 mathematically. And so we're just basically whatever line this dot product sends the most density to, whatever line of poo this is, the one that has the most in it is the one that's going to be closer to 1. But it sure as heck doesn't mean that this is 100% a cat, right? And so that's another thing that I like to put out there. Top, middle, bottom, it's now a matrix. What if we want to do digits? Can we do this with digits? Yeah. Usually we want something like int digit get picture. We totally can. the numbers are much bigger, but it's the same thing. Do you know if I run this on MNIST, I get 92% accuracy? What? Right? I'm using an atom optimizer, though, and I'm being clever about how I'm doing it. But if you run this stuff in TensorFlow, you'll get 92% accuracy on MNIST. Yeah, just this. And it's the same thing that you were able to invent in your head, which is pretty cool. So how do we get all these W's and B's, though, right? This is a good question. So what I'm going to do is I'm going to explain calculus, but to people that don't, but this is how I explain calculus to people that don't know it. And because I'm like 5 years old, you're going to get why I do it this way. So what we want to do is we want to minimize the amount of mistakes we make when we choose these W's. You were able to choose W's in your head because there weren't so many. Now imagine there's 10,000 of them, right? And then there's 50 columns and 1,000, or whatever, right? And so that's a bigger problem. So what we want to do is we want to find a way to measure how bad we are at this. I like to call this the sucky function, but not to my superiors. I call it the cost or loss function because that sounds fancier. But this says how sucky are we at it, given our choice of parameterization. There's our h of x. The answer is y. That's the right answer, and we subtract them. So if we predict the right thing, like say we guess the answer is 1, and then the answer is actually 1, this equals 0. But anytime we make a mistake, it's not 0, and then we square it. And then we find the mean. This is the sucky function of this thing right here that we just invented, right? The thing about this is I'm going to, wow, we just went away. I am going to go back to this thing, right? I'm going to say that this kind of looks like this function. Do you remember this function from a long time ago, the parabola? So, and this is how I explain this, how we optimize it to people that don't know what it's doing. You all know what it's doing, but now this is another tool. Because people are going to, I'm telling you, people are going to start asking us, how does this work? Because there's going to be regulations coming out soon about how is this even happening. So this is what I tell people. So imagine you're Mario from Super Mario Brothers, right? And you're standing on x equals 3. And you're like, boy, I sure would love to live in the valley of happiness, right? How would you tell him where to go to the valley of happiness if he's blind? What would you tell him? So Mario's sitting there, and let's pretend you're Mario. What would you do to figure out which way to go? Well, I'd put my foot back, I'd put my foot forward, and then I would see which way is going down. In other words, I'd measure a little bit of the y, I'd measure a little bit of the x, and I would divide them, maybe, dy by dx, and then I would find this slope that tells me which way I need to go, right? And then for all of you smart people, we make these go to infinitely small, and that's basically all of calculus. Well, differential calculus. And then we do it in multiple directions. So here's an example. Everyone knows that the derivative of x squared is 2x, and the way I know, again, is because I'm 2 years old. Basically, when I look at polynomial differentiation, I look at the top number, and I learned that they move to the front. And the people that are left over are so sad that they lost one, so they lose one. And so that's how I do it. So the derivative of x cubed is 3x squared, etc. There's others you have to memorize. But take a look at this. And intuitive, this actually works. When x equals 3, right, the value of the function is 9, because x squared is 9. The value of derivative is 6. So it's a positive number. Which way do we want to walk if you're Mario? Well, you want to walk in the negative direction, so we subtract off the derivative, right? So what's 3 minus 6? Well, we're at negative 3. Okay, let's do it again. Negative 3. The squared is 9. The derivative of this function at x equals minus 3 is negative 6. So what we'll say is minus 3 minus 6, right? Because we got to subtract it off. What does that equal? 3. Okay, we're at x equals 3. You see the problem? So what we have to do is we have to take a scaled version of that step, or we'll miss the bottom, right? We call that the learning rate, right? And this algorithm is called gradient descent. Well, Now it's called gradient descent. Because we're basically doing it in a bunch of directions. So the workhorse of all of deep learning is gradient descent. You're like, well, I use Atom. It's basically a variant of gradient descent that's a little bit smaller, because gradient descent tends to swing wildly around the space, and then Atom does some other things that are smarter so that it goes to the solution faster, right? And so basically, we have this huge for loop that's taking all of the data and the answers. It's looking at the current parameterization and subtracting off a scaled version of the gradient or the derivative of that function so that Mario can find the value of happiness. Okay? This is the derivative of that thing. You probably noticed that I made a mistake. There should be a 2 over n, but it doesn't matter. It's just a 2. Nobody cares, right? And here's the gradient with respect to b. And so you're doing this for the w and the b. I implemented this in NumPy, and it comes up with the right answer. Like you don't need a framework for this. It's just math, right? It turns out that all of those other frameworks are just math too, but they make things a little bit nicer. And so for this, if you look at this thing, it kind of reminds you of something that looks like this, right? Where you have the input, the input x's, right, that get multiplied by a bunch of w's and then output a number between 0 and 9. Are you following me on this? Because this is the part where I lose some people. So basically, these are all the pixels, the values of the digit. We multiply them all by w's and we add them up and they turn out into these nodes, right? And each one of them, the one that has the highest density at the end, that's the one we guess. Right? Is this deep learning? It's not a trick question. Right? Most people will tell you no. It's basically a linear model. But what if we stack them? Is this deep learning? No. That was a trick question, because a linear combination of a linear combination happens to still be a linear combination. You can prove this inductively. It's pretty easy to do. You actually have to add something in between to add a nonlinearity to make it do that. Right? And then this is now neural networks. So basically, we've gone from first principles all the way over to something like neural networks. Right? And here's the thing that frustrates me, right? People make this out to be so magical, but it's not. It's basically just math and optimization. It's basically linear algebra and calculus and optimization theory. And so you see this, these neural networks are pretty powerful, right? And they do a lot of things. Now, here's the beauty of this thing. How do you find the derivative of something as clunky as this? Well, there is something in calculus called the chain rule, which says that the derivative of a composed function is the derivative of the outer times the derivative of the inner. So when you look at this thing, right, you're basically feeding numbers to it to get an answer. Then what you're doing is you're finding the derivative of the cost function with that answer, and the derivative of this bit is the derivative of this times the derivative of this, times the derivative of this, times the derivative of this. It's almost like you're going forward to solve it and backwards to differentiate, right? And that's where it's called back propagation. You see that? And it's pretty simple now that you see it. I always think of, this is going to date me, but I watched Knight Rider as a kid, and they had that little thing in the front of the car, be like, zoom, zoom. I always think of Knight Rider. That's what it's doing. It's Knight Ridering its way to the Valley of Happiness for Mario. But I don't explain it that way to professionals. Well, except to you, because we're all friends and we shut the door, right? This is what this now starts to look like when you're starting to small it down, right? This is a matrix, right? You multiply the input digits by this matrix, dot product it out, you do a function over the answer, and then you do it again. You do a function over the answer, then you do it again. And then you softmax so that it sums to 1, and then these things start to look like probabilities, but they're not. But we will tell everyone that they are, because that's what we do. But not yet. I didn't get there yet. He's where are the convolutions? They're coming, sir. I know you came for the convolutions. I saw it in your eye. When you watched, he's like, convolutions. Yeah. How do you do this in TensorFlow? Most of you maybe use TensorFlow. I like to think of TensorFlow as like 3 different things. You craft a function shape. In scikit-learn, you basically pick one. You don't make one. You pick a function shape or a model. You optimize the function or the model using a cost or loss function and an optimizer. In my case, that thing that I showed you was mean squared error. It turns out that categorical cross entropy is better for the digits one, right? And then you pick an optimizer, right? I showed you gradient descent. Stochastic gradient descent is when you batch everything up, right? And then you use the model to predict. The model again is this function. The loss function is how sucky we are. I already did this bit. Here's what it looks like in TensorFlow. It's pretty nice, right? Keras. Before Keras, this was kind of a chore. Did anyone ever? Oh, yeah. I think PiTorch got it right before TensorFlow did. No offense. And I'm an equal opportunity person, right? I was in Israel once, and I was doing a talk on TensorFlow, and they're like, Seth, aren't you from Microsoft? That stuff's from Google. I'm like, yeah. We don't care what you run in our cloud. The slower, the better. Cloud cost joke for you all. Actually, TensorFlow it's really nice. I really like a lot of the stuff they're doing with their data sets. Before, I didn't like it in TensorFlow 1.0. I was really ticked off at their data sets. So I wrote it off and went to PiTorch, and then now I'm coming back. And so you can see all of this here. Now, the thing is that these are all the optimizers. These are all the loss functions. Here's all the models you can build. And I'll get to these a little bit later because you, sir, very adeptly said, what about the convolutions? I'll get to them. So the question always gets to people when I give this talk is like, which one do you pick? Let's talk about data science and the loop of sadness. Right? This is our data science loop of sadness. So when they ask me, how do I know which one to use? I say, try them. What if it doesn't work? Try a different one. How long does it take? Go ask your data scientist whose door is locked right now. Yeah. Yeah, it depends on if you're using they were nice to me at Microsoft. They let me, this has a 2080 RTX in there. I know. I can run MNIST at a second per epoch. I know. I'm all of a sudden I see all these hungry eyes and not for the pizza. Holy cow. Right? And so this is the bit that people don't understand about development. And if you look at data science code from professional data scientists, you can almost see where they changed their mind in the code. Right? And that's why people complain about data scientist code. I say, slow down. Data scientists don't write code to put into production. They write code to prove that a model will work. So step off. All right. So let's talk about another thing. What I did, though, in this case, is I forced the digits to all be on a single line, right? Because I forced it to be a linear model. Did you see that? But it turns out that there's some relationships here that are actually quite useful, like this way that it's losing. So how do we do that? Well, let's talk about filters and pooling. So a filter is actually a very interesting operation that you would think doesn't do anything, right? So for example, here is what this filter does. Basically, we're going to take this, oh, I did the wrong one. Erase. We're going to do this box right here. We're going to dot product it with this box, and then we're going to put the answer here. And then we're going to do it again here. And then we're going to do it again here, and then we're going to do it again here. I'm just explaining what this is doing, and I'm not telling you why. I'm just telling you what it is. I'll show you why in a second. And so we get 4 numbers. But this is not good because it destroys the image, right? We're losing pixels around the edges. So you can do this thing called padding. Padding. It's called same padding, by the way, if you're using it. Now when we do it, notice that we get the exact same amount of pixels back that we want, right? Cool. Let's talk about pooling and stride. What if we want to make the thing smaller after we've done the little filterings? So basically, this is called a pooling, where we're basically taking this box and we're putting the biggest number in here. We'll take this box and we'll put the biggest number in here, and then we'll do that again, right? And stride has to do with how much do you move over, right? So are you going to move over just 1 pixel at a time? Now, you might be wondering, what does this actually do? right? I will show you. So basically, I wrote a crop and resize, and I wrote a convolution in NumPy, right? Because everyone has all sorts of spare time, right? And then I also wrote a pooling that takes the max out of it, right? Max pooling. So by the way, that filter is also called a convolution. Well, I said that too fast. Now here is the same. Remember how we did 1, 1, 1, 0, 0, 0, minus 1? I decided to try that one out to see what happened. And what I did is I took some important pictures that matter to me, and I'm going to go ahead and try to run, like these are important pictures, right? You saw wedding and thought mine, right? Look what happens when I do this convolution over this image. Pow! What did it do? It found the edges without me doing anything. What happens when I pull it? Boom! It enhances them. So you know how back in the day when you'd watch like CSI Miami and they were like, zoom, enhance, and you're like, that's stupid. Turns out they can do that now, right? Sounds stupid. But that's what this was doing. What this is doing is this is enhancing an aspect of the image. Let's do it with another picture. Here's some of, again, these are important pictures to me of the kids. And let me do one that actually makes sense, a fence. That's crazy, right? That convolution is doing that. It's basically creating a new picture for you. And it turns out that when you look at this operation, it's a different form of the dot product. It's just rolled out differently, right? And so when you make these things, you can actually create these convolutions, which are matrices, that go over the image and are making a new image for you. They're basically making new images for you. Now, what images is it making? I don't know. It's making the images that make the optimization work better. And so it will choose these for you. And so if you do this style of thing, you get like 99% on MNIST, right? Or something higher. You're basically doing two convolutions, a pooling, and a RailU over them, and then a softmax at the end. But you always unroll it with imaging, with computer vision. You always unroll it so that it does something like this, right? And so these are called convolutional neural networks because these convolutions, what they do, especially with images, is they're able to generate very complex images. And you've seen them like where at the bottom it's like it found this edge, and then up in a layer it's like it found a nose. What? Right? Because it's basically generating new images as it goes along. Now, the problem I have with this is it seems awful magical, like the computer is learning about noses. It isn't. These things are not intelligent. I had a guy argue with me. Like, this is what he told me. He was trying to say about like AI rights, you know, like, and I was like, it's a computer. It had like Seth, you're talking like we used to talk about animals. It's a bunch of numbers in a friggin' network. It has no feelings and no thoughts. Like you're thinking, but what about the ones that generate art? Seth, they're just transposes of these things. Right? Because they generate images forward. Right? It's a transpose convolution which generates a bigger and I didn't even know how to respond. I was like, oh. Do your computers have names? Mine do. I name them after Tolkien characters, incidentally. The cloud, though, right? How am I doing on time? Oh, I'm doing pretty good. The cloud, though, how do we do this in the cloud? Well, here's the thing. This is the way we do it on Azure Machine Learning, but look, the thing about Azure Machine Learning that I like is that you don't have to use all or nothing. You can use it just to register your models, and that's it. Like, do you version the models that the machine learning algorithms produce? You should. Right? Usually as data scientists, we're like, hey, I made a new model. Where is it? It's on the share. And then you have to go home and take a long shower, right? Because you know you put that on the share. People are looking at that file that you put it there, right? And that's a problem. So you can use it to register and manage models. You can use it to have images of your things. You can use it to deploy. You can use it to prepare data. You can use any of these, whatever you want. Like, this is, just use what you want. Use what you like. If this adds benefit to you, great. If it doesn't, great. Tell me why, and I'll go tell them at the home office, right? Hey, this stinks because Bill at the Toronto AI user group said this doesn't work for me because of this, and we want to fix it. Here's what it looks like when we actually, here, I'll just go to it. Here. Oh, I went too far. Okay. So if you take a look at this, this is our Azure Machine Learning Studio where we do a bunch of stuff. Now, if you're a data scientist, I'll give you an example. MSR once gave me some code, it's Microsoft Research, that generated like novel pictures of birds from text that you write. Like, this is a blue bird. And it would create an image of a blue bird, right? It did some cool GAN stuff. I didn't know about it at the time. But as I looked at it, I realized he was using like a really weird version of PiTorch on Python 2.6. Like, any of you that have had any experience playing with Python on your machine, it's a dumpster fire, right? And maybe I just suck at it. If any of you are like, no, Seth, it's not, come afterwards and educate me, seriously. Because I've had a lot of problems. And on top of that, I've had a lot of problems because I use Windows. Just leave it there. Just let it hang out there, right? It's getting better, right? So he gives me this thing, and I'm like, how am I ever going to run this? Well, and I thought I'll just use a container. Do you use containers when you do your machine learning stuff? It's nice, right? It sucks right now, and I keep fighting the OS people. You need to give me GPU pass-through on my container. It's partly our fault too. And I keep telling them that. They're actually working on WSL, Windows Subsystem for Linux, GPU pass-through. So they are going to work on that. So that would be super nice, right? But I just want a straight Docker, let me hit the GPU, because if you've ever run stuff without a GPU, right, you have nothing to warm your hands by in the dead of winter, right? Oh, it's running, right? So basically, here's the thing, and the reason why I bring this up is because there are certain things that we should just share as data scientists. Like, what data sets are we using? In Azure Machine Learning, you can create data sets and version them. So that means that you're like, well, how come your model's better? Well, I'm using version foo of data set, right? You can keep track of your experiments. What is an experiment? It's a training run. Not only that, you can rerun it exactly the same way anybody else ran it, right? Which is really cool. You can also create pipelines, right? For those of you that are familiar with Kubeflow, it's exactly the same, but we add a layer of SDK over it, where you don't have to do like container ops, and you don't have to know about Docker. You just say, here's my code, and here's my environment, do it, right? We have this notion of models, where you can store and version your models. And we have these notions of endpoints. There's two kinds of endpoints for us. There's the endpoints for inference, and there's the endpoints for rerunning machine learning pipelines. Why would you do that? Well, because of data drift. What if you wanted to unstale your models every week and rerun a pipeline? You basically just call the thing. And the cool thing about these pipelines is it will retain information that it's used before. So if the parameters don't change, it won't rerun that section of the code. And you know that this can be very costly. Like, if you're rerunning this step and it's converting 2 terabytes of images into 1 terabyte of TF records, you don't want to run that every time, right? And so it's able to know if the parameters don't change, then these things stay the same. You can do that. And that's what the endpoints are for. Now, here's the other things for managing. We have shared compute and shared data stores. You're probably wondering, what is the difference between a data store and a data set? Great question. It's like the difference between a hard drive and a folder for data science. In this folder, this is this data set, right? The data store for us is basically Azure storage. You could just dump everything there, and you can run these algorithms. And it's all happening in the cloud. And here's the cool thing that I didn't tell you. When you run the experiments, it will mount Azure storage as if it was part of the hard drive. It's crazy, which is really cool. Okay, so now I'm to the part where I'm going to answer any questions you have about what I've told you so far at Azure Machine Learning or anything. So are there any questions? Okay, we good? Did I scare everybody? Okay. So now what I'm going to do is I'm actually going to make a model. By the way, I talked about all these things. They're pretty cool. So I'm going to do a more complex example. And obviously, machine learning is wonderful and deep learning is awesome. So I'm going to apply this to a love of mine, which is I'm going to make a convolutional neural network to detect whether it's tacos or burritos, which is an important data science problem, right? Because there is some general world confusion, and we need to fix it. Okay, so I did this thing here, so I can stop that. So what I'm going to do is, is this the right one? No, I went to the wrong screen. This is the right one. Okay, so what I'm going to do is I'm going to show you a 3-step process with TensorFlow to build this model. So what I'm going to do is I'm going to show you it already ran. So let's go to the experiments here, and I'll give it a second to load. Here's the latest run of my sear experiment because it sees Mexican food, which is really important. And what you'll see in a second as it loads up is you'll see the 3-step pipeline that we do. And the pipeline is basically prepare the images, do the training, and then register the model. And hopefully there it is. So you're probably wondering, well, what preparation are you doing for images? Well, these things are fairly finicky. Like if someone puts an alpha channel in one of your pictures, boom, right? Because I planned for 3 RGB, right? And sometimes in some models, they switch the channels or they put the channels first, right? And you're like, right? And so you have to pre-process this stuff a little bit. And so what I've done is you can see in my prep, I'm basically using TensorFlow, I'm basically looping through all of the files and pushing out TF records. And you can see here in the data, when I do the prep, it's basically a bunch of TF record files. Anyone used TF records before, by the way? Let me explain what TF records are then. TF records is just basically a way to store tensor data in an intelligent way. Do you want to add anything? Because maybe you know more about TF records than I do. Oh, good. I'm always worried that more people know more. I actually know a lot of more people know more than me, and so if you have something to add, please add it. So basically it's taking all of these images, resizing them to the appropriate size, making sure they have the right channel ordering, and then stuffing them into this TF record. And the reason why is because it makes it easier to train, and I'll show you shortly how. Once this data preparation step stops, and by the way, in Azure Machine Learning, when you do this stuff, we actually store that all these steps were run, right? And this data source is the parameter. So I can change where it's sourcing the data from at any time, and it will load different images, right? And you can see here, you can look at all the details of everything that happened. Here's the snapshot of the code that ran. Here are the logs that it output. Like this is literally what it did. So notice that now, because I'm running it in the cloud, you have visibility and traceability into what actually happened. Because usually you just run it on your machine, which is nice, but it doesn't play well with others, right? And now as you're noticing, the data science practice is involving now bigger teams. How do you interact with them appropriately? What if Sally left because she's the best data scientist you have, and then Bill comes in? Bill usually starts from the first, as a data scientist, I'd be like, okay, let me try logistic regression, decision trees. If it doesn't work, then let's go with something else. But if Sally already did that, and you can have a record of the experiments that happened, Bill can start at the right spot, okay? And that's what this is all about. When you're doing model training, for example, in this case, when it loads the detail, there's a way, and let me get to the model, because I didn't show you the actual training algorithm. So this is the prep step. By the way, if you're wondering, I want access to this, if you go to github.com, and then go to Cloud Scale ML. It's under this thing called sear, and so everything is in here. You can totally do all of this stuff. If you want, I can run it on my machine right now. I can make it run on my machine. Here, let me do that so that you can see. LS ls. So run. Oh, sorry. Conda activate tf run. Oh, that's not the one I want. Which one is it? Pipeline. Dot command. It's going to delete all those folders, and then we're going to heat our hands by the. But here's the thing: I can run this all in probably under 5 minutes. Right there, it's building the TF records. Right, taking burritos and tacos and making the TF records, and this is going to take a while. Well, not too long. It's probably like 600 images. It's not that much. And I'll let it do that, so you can see that I am running it locally. Right now, you're not going to hear the GPU, but you will. And it's here we go. We're getting into it. Yeah. Oh, did you see this beauty? Look at this. Look at this beautifulness. That's cool, right? So yeah, you can run it locally. But who's going to know I ran this locally? How am I going to share this work with other people on my team? Right. So what I'm saying is, as I said before, since all of this stuff, basically, like when it comes to Azure, you can use whatever you want. You could do the logging directly from here on your local machine and log to Azure Machine Learning so that you can have stuff that looks like this. Well, I'll give it a second to load up. But basically, if you log, you don't have to run it. I don't care where you run it. Use just the logging mechanism of the experiments, and you can log all of the metrics there. So for example, here is this one that I actually ran this one in the cloud, but let's just say you ran it locally and you logged out. In this case, I don't have it logging because it's running in an offline mode, but basically now you can track anything. For example, accuracy, loss. This is what I'm actually logging, and you can log it out as a chart or as a table, and I don't know why things are taking so long to load up. But basically you have a chart of the accuracy of this model and the loss function of it. So don't just do the logging here. Or maybe save the models there. I don't care what you do. Like, as long as I'm solving your problem, I'm happy. So if you have fantastically good machines, yeah, the way that you log these things, hold on, looks like there's no data in there yet, because I actually reran it, unfortunately, when I did the other one. So let me show you how this actually works for training. So, and you're probably wondering how the logs happen, and you can take this file. So basically, in this case, when I train, and this is why I really like TF records, is because now you can do something like this. This is the training data set, right? And what you can do is you can create this TF record data set with this train array. And basically, it's an array of the name of the files of the TF records. And now you can do some crazy stuff like, here's the parse record to pull out the vectors and the matrices. Here's the number of parallel calls we do. And it creates this pipeline of data that you can use when you're training. It's actually really cool. And usually I skip over this bit because the people I sometimes talk to don't understand this bit, but you do. This is why I'm starting to like the front part of TensorFlow. You can see here that I am model stealing, otherwise known as transfer learning. Right? I'm taking MobileNet and I'm just putting it into a sequential model with an output on a softmax. Right? Which is kind of cool. And then you can see here that I'm optimizing this stuff. Now here is the bit that's interesting that gets to your point. How do I log this stuff, right? Notice that I have a couple of callback things. One is called the model checkpoint, so that it just outputs models whenever it has one. But here's one that I created called an AML callback, right? And notice that it's called log AML. And notice that on the callbacks, when I do the fit, I'm passing log AML in. What does this do? I'm glad you asked. It turns out, and this is code that I've never shown you, so I'm so happy that I get to show it to people because nobody looks at this. Basically, an AML callback is an implementation of a callback function in Keras that says anytime something is run, log it to the AML run. So if I put that callback into my Keras, fit, it's basically going to shoot metrics up to Azure Machine Learning, like TensorBoard. Yeah, you can make it so that you can create a new run and run it locally. Yeah, that's a good question. And so you can shoot that up. And if it doesn't work, let me know because they told me it does. run it on your local machine, but log up, right? And now TensorBoard is awesome too. And if you're doing TensorBoard, you can actually save those into the output folder of your run on the actual cloud-based one, and then you can call TensorBoard on the run in the cloud, or you can just run these, do these metrics, right? Now the thing is, again, when I say I'm serious, this is a buffet. You take whatever you want. If you're just going to have the salad because that's what you want, great. If you already have powerful machines that do the thing, I'm a fan. But you can use other aspects of this stuff that may be helpful. And if it's not helpful, then I want to know why. Great, tell me why. And I mean that honestly. So great question. This is, again, you can just take this. Notice that the AML callbacks are using just they're just inheriting from the callback keras function, and these are just the things that I override. Like when the batch ends, I'm gonna log all the metrics. All right. And note. So I'm using whatever the TensorFlow data set does with a TF record set. Whatever it does, it does. I'm not doing anything more than that. So I don't know how it does it. All I know is that when I create a TensorFlow data set, I'm using TF records. What it does with memory, well, I guess I do know a little bit. You can notice that when you're looking at TF records, it's pretty smart about how many it's pulling out. And so it loads it up from memory, and then I have this map function which parses the TF record into a batch output, right? And I'm doing 5 parallel calls, and so it's basically has a memory pipeline of things that it's queuing up for it to do. And then it shuffles it. If the buffer size is 10,000, that means it needs to load up 10,000 records to do that shuffle. And then I create the batch size, and then I buffer prefetch by a buffer size of 5. So depending on how you order these, it will do the thing. And if you look at the TensorFlow documentation, it'll tell you about this. I'm not doing it. I'm just letting the framework. Because now notice you're getting to memory management and stuff, and so that's how it does it. Okay, so this is how I do the thing. And then the last thing that I do, and this may be a part of your workflow as well, is I am basically doing where's the model register? The last thing I'm doing is I'm basically finding the best model that it output, and I'm just saving it to Azure Machine Learning. If you only want to do this bit, great. Now you can version your models. And now what you're probably thinking, well, is a model a single file or is it a bunch of files? The answer is yes. Do whatever you want. For example, PiTorch YOLO happens to be, in its implementation that I've seen, it's like 4 or 5 files. So you put that all in there, right? And so the question is, well, how do you use this when you're actually going to run it? In Azure Machine Learning, we have the endpoints that you can create, and all you need for this is a Python file that has an init and a process and a run. And basically, the raw data comes in. You load up the model in the init so that it can store it in a global model, and then you just run it. And I could just run this locally, and you can see it will do it. But you can put this in as a service as well.
Hello and welcome to this special edition of the AI Show, where we've got a special guest, Jeremy Howard. We're going to talk about how to actually build applications, AI applications, without really needing a PhD, something I don't have. Jeremy, why don't you tell us who you are and what you do and how you got involved with AI?
Sure. So I'm the co-founder of Fast.ai. Fast.ai is a research, teaching, and development lab based in San Francisco. And our specialty is deep learning, and specifically about making deep learning more accessible. We've been doing that for a few years now. We have what might be the most popular course in the world for deep learning. We have one of the world's most popular software libraries for deep learning. And our research have developed some of the world's most important new algorithms for deep learning. And we also have a fantastic community of tens of thousands of people who help each other out and help me out on our deep learning journeys. It's been a real pleasure, and it's been exciting to see the impact it's had so far.
So how did you get involved with AI and specifically deep learning? Look, I went to school when SVMs were all the rage, and to me, they were beautiful because mathematically they were, convex functions, and it did really cool stuff. How did you shift over to the world of deep learning?
Sure. So I was kind of the opposite. I guess, well, I was, 10 years ahead of that maybe. So I was kind of starting my working life when neural nets were last huge. And I was using them in banking, I was using them in marketing. I thought they were fantastic. But we had to spend literally millions of dollars to get custom silicon to do anything at a working scale. And then kind of SVMs came and killed neural networks, because for the reason you mentioned, all the people with bigger brains than me, folks like you that understood all the math, went, wow, these are mathematically very attractive, so I'm going to focus on this. Whereas to a kind of boring software engineer guy like me, I was kind of like, yeah, they don't work very well. They don't predict my marketing outcomes very well, or they don't predict the financials very well. So I put everything aside for a while. Then in the kind of early 2000s, random forests came along, and that was like, okay, this is back in my territory. A simple thing, I can code it up into hours. It works great. And so I was the president and chief scientist of a company called Kaggle, which is the world's largest data science community and a competition platform. And I kind of had this unique position there where I saw all the competitions coming in, I saw all the winning solutions, and I saw deep learning suddenly started taking over. And I was like, oh, hooray, neural nets are back and they're working. So I quit Kaggle and decided to really focus on what I've been waiting decades for, which is to bring neural networks back.
Now, the interesting thing about neural networks is whenever we talk about deep learning, there is this baggage of, and I know in America we say math, but everywhere else they say maths, because it feels like deep learning has a lot of extra maths. Yeah. Is that a warranted thing to assume that there's a lot of math baggage in there?
Yeah, so it turns out there's not. So I don't have a PhD myself, and this has been a real boon for me in teaching, because I have to make things understandable for me, and that's a really hard task. And so it turns out that the actual math we need for deep learning, so basically you need to be able to add, you need to be able to replace negative numbers with zeros, you need to be able to multiply, and then in theory you need to be able to take the derivatives of those things, so like really simple derivatives, although in practice actually the libraries all do it for us now. So if you can add, replace negatives with zeros, and multiply, then you basically have the math you need to do deep learning.
So you've spent a lot of time, it feels like, trying to get people to understand these primitives, but in a unique way. Tell us about the goal of Fast.ai, and what are some things available to people right now that they can go look at?
Yeah, so let me explain how we think about this. And the way we think about this is heavily influenced by expert educators like Paul Lockhart. The kind of real top educators say that the way you need to teach somebody something is to give them context and get them in the game. So in other words, you need to say, this is why you're learning this, and let's go ahead and use this thing you're learning right away to do something you care about. So the vast majority of deep learning and technical subjects in kind of more numeric subjects are not taught like this. It's kind of like, okay, let's do a year of linear algebra. Now we'll do a year of calculus. And then, we might finally then start to learn about the theory of neural networks. And then in your graduate degree, we might let you write some code. So our approach is the opposite, and it's much more like the way, Microsoft would teach, like, here's how to get going with Visual Studio. It's like, okay, start Visual Studio, type this, press run, and look, the thing pops up and you've created an application. Now to deploy it, click over here and press publish. Now people can use your application. So with our approach, with our book and with our course, within the first half hour, you have created a pretty close to state-of-the-art vision classifier yourself. And by lesson 2, you've written a new vision classifier that no one's ever created before, especially using your own data set that you actually get with the Bing API, and you deploy it for anybody to use as a web application. And so then we have the context, we have the motivation, you're building stuff that matters, and then we say, like, okay, here's a problem. It doesn't understand this category very well, or it doesn't handle false negatives very well. How do we solve that? And then we'll say, right, well, to understand why there's that problem, we need to understand this little bit of math. And we'll say, like, okay, here's this little bit of math to explain everything you need to know. And so here's how we convert that to code. And then here's how you can see that code lives in the library. And then here's how we can use that to solve the problem. So every time we learn a piece of math or a new piece of code, it's within the context of solving a problem. So by the end of the book and by the end of the course, you know a very wide spectrum of kind of deep research topics in deep learning. And a lot of Fast AI alumni have ended up presenting papers at the world's top deep learning conferences like NeurIPS and so forth. So it really goes deep, but the whole time it's motivated by practice.
And I want to like, look, I have the book right here. I went through it just a couple of days ago. And the reality of the matter is, literally in chapter 1, you are building, and I'm going to try to open the page. It literally says, your deep learning journey. There's my camera. And you can see, like, literally, it says your first model, and you're starting to classify pictures that look like this.
Right.
And so, and this is not how I was taught.
Right.
But it feels like providing context up front is super helpful. Are you finding success with the people that are taking your course on Fast.ai with that?
Very much so. I mean, it's a real problem that the people that teach technical topics like deep learning are the people who have had successful academic careers. And so these are the people who found the traditional approach to teaching technical subjects quite adequate. The kind of bottom up, start with, you know, the math and then spend years and years before you start actually using it in practice. And that means that, yeah, teachers are different to the rest of us. So we tried to build something for the rest of us, for people like me. You know, I didn't have that technical background. I was straight into business when I was 18. And so it's been amazing to see how well it's worked. So for example, in a lot of business and scientific domains, it's kind of taking over. So for example, in protein analysis, so many scientific papers are now being written by FastAI alumni using the FastAI library. We see in business so many CTOs and so forth from insurance companies, from banks, from telecommunication companies are contacting me and saying, "Thank God for your course and for your library. Everybody who joins our organization, you know, has to do the course before they start, and we find that everybody hits the ground running." You know, even places that you might think are pretty full of PhDs anyway, like Tesla. You know, Andre Karpathy, who runs the AI group at Tesla, told me last time I saw him, "Hey, you know, everybody who joins this company in my team, I tell them, make sure you've done the Fast AI course." I know at OpenAI, which is a very popular research lab, a lot of the residents in particular, you know, are told to do the Fast AI course first. So it really is, it's really working great. I couldn't be happier.
And this is cool because it's an interesting distinction between what a scientist might do to push the envelope forward and what an engineer might do to actually make something work. And you're seeing that success. So we talked about Fast AI. We talked about the course for where can people find the course?
So they can go to course.fast.ai. The whole thing's free. There's no ads. In fact, everything Fast AI does is free. Because it is a self-funded lab, we have no business model. It's just entirely an altruistic exercise. So it's all out there for you to take and enjoy. And all we ask is that you give back by telling others about it and helping out, you know, answer questions in the community and so forth.
So I want to make a distinction with Fast.ai as an organization that puts these things together. The course where people can go and take, but then you mentioned something about a library. Tell us a little bit about the library for Fast.ai.
So our goal is to not need any code. So that's the ultimate in accessibility, right? So our kind of first step was to say, very, very, very few people in the world are expert mathematicians. Relatively speaking, far more people are expert coders. So let's first of all build something that expert coders can do. So the current Fast AI offerings are designed for people who are very comfortable coding. And then our next step is to kind of say, okay, now there are far more people that don't know how to code and aren't expert mathematicians. How do we get to them? And the eventual goal, therefore, is to get rid of code entirely. So our kind of intermediate step there is to make the code like easier and easier and easier to use. Now, we build on top of a library called PiTorch, which is by far the world's most popular library amongst researchers, and it's by far the world's fastest growing library. for deep learning. I think for that reason, because whatever the researchers are using is what everybody else eventually ends up using, because the researchers build the stuff the rest of us use. Now, PiTorch, as you know, Seth, is it's brilliant and flexible, but it requires a whole lot of boilerplate. And coders like me hate boilerplate. Boilerplate is particularly problematic for stuff like deep learning, because every line of code that you don't really have to write is a line of code you can get subtly wrong. And unfortunately, in deep learning, you don't get an error message. You just get an accuracy that's like 2.3% worse, and you don't even know that it happened. So we got to get rid of all the boilerplate. So FastAI is a library that sits on top of sits on top of PiTorch, and you write only the code that the computer can't figure out for itself. So you just tell it what you want. And so it's literally 4 lines of code to create a state-of-the-art vision classifier, a state-of-the-art neural network for text analysis, a state-of-the-art collaborative filtering system, a state-of-the-art tabular analysis system. And in each case, the 4 lines of code are nearly the same, because the whole thing is built on kind of time-tested software engineering principles of consistent APIs and a decoupled design and a kind of very clear API boundaries. So for a coder, it's something you can kind of dive into pretty quickly, and then you can start to kind of peel under the layers and customize things at deeper and deeper levels as you're ready to do so.
And that's the thing I like most about it, because in my brain, because most people don't know this, but I was a dev for 10 years, and then I went to grad school to do this stuff. And so I started making these analogies in my head that a model is just a lazily written function with data. And so you should see similar steps when you're building any model. And I felt like I was writing too many for loops. By the way, PiTorch is an excellent library written by really good programmers, but I was writing a lot of for loops. I was doing a lot of data stuff that felt like it was the same. And you abstract those concepts into things like data blocks, optimization, etc.
And this is also great for researchers. So these, it turns out that a lot of what ends up in research papers is basically refactoring. And so we actually ended up writing a peer-reviewed paper about the FastAI library that really is just describing the refactorings that we did. So you mentioned, for example, the optimizer. We've built this, what is, I believe, the first, and it was peer-reviewed, so I think it's fair to say this, the first generic optimizer. So the optimizer is the thing that sits underneath the neural network training and actually makes the weights get better and better at doing whatever you want it to do. And we realized that if we looked across dozens of state-of-the-art research optimizers, and we found there was basically 2 building blocks that they all sat on top of, and we could kind of rewrite the equations in their papers using these 2 building blocks. So then we rewrote the whole lot in code. So we created those 2 building blocks in a generic optimizer base class, and then we subclassed that. We'll sometimes use composition, sometimes subclassing, to create all these state-of-the-art optimizers, often with 1 line of code or sometimes with 2 lines of code. And so it's great for researchers, because then they can say, like, okay, I wonder what would happen if we took the Atom optimizer and replaced the debiasing approach with this different debiasing approach. And you can literally just plug in the different debiasing approach. Whereas if you look at how research code was written before FastAI, people would write their own 200-line optimizer from scratch. Often they would have mistakes, or it wasn't state-of-the-art because they would miss some important thing like weight decay decoupling or whatever. So they'd spend months as researchers writing code rather than implementing their research.
Even in my fast skim of the book and looking over the library, I was super impressed, because look, I've gotten research code that's been thrown at me from like MSR, for example, and they said, hey, implement this so the customer can see how cool this model is. And it was actually really hard to see, because in research code, maybe you have seen this as well, you can see where the data scientists even changed their mind when they were writing code, and you're like, oh, this should get taken out. And when you abstract certain concepts away, it just makes everything more powerful, I think.
Yeah, exactly. Abstractions are so important. So the FastAI library has 4 API layers, and they're just different levels of abstraction. So at the top layer, we have these higher level API concepts like the data blocks API you mentioned. So the data blocks API came from me after working for more than 25 years with data and machine learning, and realizing there's this handful of things that covers the entire spectrum of everything I've ever done with data processing. So, for example, you have to separate out your data set into a validation set and a training set. You have to label it. Sometimes you have to filter it. Sometimes you have to pre-process it. Sometimes you have to do an on-the-fly transform of an individual item. Sometimes you have to do an on-the-fly transform of a batch on the GPU, so forth. So I just listed down what these things were, and we kind of saw how we can create this really simple little class called data block, where you as a user can say how to do each of those things. And we've actually been really lucky to benefit from brilliant help with that. So when I first wrote it, I used a Fluent API. So for those people that don't know, a Fluent API is that kind of where you say, like, do this, dot, do that, dot, do that. Pretty popular in the JavaScript world. Very popular in the kind of the VBA world with the Office applications. And the problem with the Fluent approach, which was the kind of version 1 data blocks, is, first of all, you don't get great IntelliSense with Fluent approaches, because generally speaking, it's going to be very hard for the language server to know, after all these dots, what kind of object is this thing, especially in Python, because in Python, we don't really have all that static analysis. And the second is like, well, it has to be in a particular order anyway. So, why kind of enforce that? So in a recent course, I was lucky enough to be joined by Chris Latner, who developed LLVM and developed Swift and developed Xcode Playgrounds, one of the best programmers I've ever come across. And him and I co-taught a couple of lessons. He brought along with him lots of other genius Swift programmers, because we did the whole thing in Swift. And we kind of replaced the whole DataBlocks API with a functional version, and also got some help from a guy called Alexis Gallagher, who's a terrific Swift programmer and author, amongst other things. Between us, we kind of built this new functional DataBlocks API. And I'm not a functional weenie by any sense, but I certainly really enjoy a lot of the benefits that it can bring. And suddenly it turns out, oh, we can bring that back to the Python world. And so FastAI2 now has this functional DataBlocks API where you don't have to worry about what order it goes in. You get IntelliSense all the time, and it actually ends up kind of more concise and more clear. So these higher level APIs like DataBlocks, for the user, it ends up being this nice abstraction where they just have to learn one concept, which is DataBlocks. And then they can do vision, text, medical imaging, tabular, whatever. And then that is built on top of another level of abstractions, which is the mid-tier API. So the mid-tier API is the API that we build the higher level abstractions on. And when you want to change the higher level abstractions, you can use the mid-tier API. And that includes things like transforms and pipelines, kind of lower level stuff. And eventually you get all the way to the bottom and you'll find our optimized GPU primitives. So for example, we wrote our own computer vision library from scratch so that all the transforms actually run on the GPU, which turns out to be really important, because nowadays a lot of people find their training code is actually the bottleneck is not the GPU, but the CPU, trying to get the CPU just to deliver the JPEG decoding fast enough, or deliver the rotations fast enough, or whatever.
And that's quite interesting, because I mean, when you're, for example, to augment your training data, you're going to be doing some transformations on the images anyways. You might as well do those on the GPU. Well, this is very impressive. Like I said, I briefly looked at everything, and I was really excited about some of this stuff. I love the expressiveness of the API. We're sticking with programmer type concepts of convention over configuration. And if you want to dive in, you certainly can. Where can people go to find out more? Let's just give them those 3 links and put them up again.
Yeah, so for learning more about the library, go to docs.fast.ai. So docs.fast.ai is where you can learn about the library. You can get started. And one of the really cool things is the entire library is actually built with notebooks, with Jupyter notebooks. And so every documentation page actually is the tests, and is the documentation, and is the implementation. So you can click on any page. At the top, there'll be an Open in Colab link. and it'll pop open that documentation page with actual working code examples that you can play with. So it's a really nice way to see exactly how things work.
Well, this is really cool. Again, for those that don't know, there's a book also. It's pretty good. I leafed through it and I was very excited about learning more. Now to finish up, I want people to get a sense for your thoughts on the future of deep learning and AI in general, and then we'll close up.
Sure. So I really feel like deep learning, it's another way of building programs. And if we go back to machine learning was developed in the late 50s by a guy called Arthur Samuels. And Arthur Samuels actually made a prediction that one day there would be very few people writing step-by-step code with loops and variables and conditionals, but instead most code will be kind of learnt code. It'll be machine learned code. My guess is that's where we're heading. I think when I look at a lot of the code that I write, I realize a lot of it could actually be automated. A lot of the outputs could actually be automated. Now, one of the concerns is that people think to use deep learning, I need lots of compute and lots of data and a PhD and all these, abstractions. And our focus has been to make sure that's not the case. So we've actually built state-of-the-art competition-winning algorithms that have beaten the world's biggest companies at performance in machine learning using a single GPU with folks that are students with like 3 months of expertise. We've got students that have built really practically useful models with less than 100 images. So, really what I'm saying is deep learning is here to stay. It's going to get bigger and bigger and more important, but you can absolutely get started with it now without huge data sets, without huge computers, and without years and years of linear algebra study.
Well, Jeremy, this has been amazing. Thank you so much for spending some time with us. Again, the book, Deep Learning for Coders with Fast AI and PiTorch. If you have the time, make sure to go get it. And if not, go to
Seth, can I mention,
yeah.
That book is also available for free as Jupyter Notebooks. We wrote the whole thing in Jupyter Notebooks. So if you go to our GitHub repo, there's a repo called Fastbook where you can read the whole thing for free. But, buy yourself a copy as well.
Hello, my friends. I'm super excited to be here. My name is Seth Juarez, Principal Program Manager for the AI platform at Microsoft. And today, my friends, we're going to be talking about MLOps, doing the things to preserve tomorrow's machine learning sanity today. And now here's the thing. Machine learning is fun. It's awesome. But there are just times where you just want to punch it in the face. And the reason why is because there's just a lot of process. So today we're going to talk about what MLOps actually means. We're going to talk about 4 tips on how to make it a little bit better. But I thought before we did that, we'd go ahead and start with the problem we're actually working on. Now, it's not like an innovative machine learning problem. It's not the greatest thing ever, but I thought I'd show you for a second what it is that we're doing. So let's go to my HD webcam. There I am. You can see me in this one. Now what I'm going to do is I'm going to tell you a little bit about the app we're building through this other camera on my browser. What we're building is a rock, paper, scissors game where I can just be like 1, 2, 3, rock, 1, 2, 3, scissors, and 1, 2, 3, paper. Now the idea is I want to be able to just use my hand gestures to play against the computer. I haven't built that other AI yet. We're building the classification model for a simple problem, super easy. Let's go ahead and see if it works. So here's the inference time. There it is. Looks like it thinks my face is rock. Okay, happy about that. What about this one? No, scissors. Ugh. So friends, looks like it's guessing rock a lot. One thing I want you to notice is that we deployed this thing a little earlier today. We're going to see if we can make that change a little bit. So this is the thing we're working on. It's a simple classification problem. and I want to make it work. Let me do this at the beginning of the session just so we know what's going on. Let me go ahead and open Visual Studio Code, and let's change this. Let's use a ResNet. So ResNet 18 as the base model. So there's a ResNet 18. I'm gonna go ahead and copy that, and let's check this in because I think this is gonna be a little bit better. So let me add this, and we're gonna say trying a ResNet 18. So we'll commit that. It brings up a dialog for my password because I sign all my commits. And now let's go back here and sync the changes. Okay. So we've made a change. We're syncing the changes. We'll see if this is any better. All right. So let's talk about what MLOps actually is, because I think it's hard to explain. So what I'll do is I'll start with DevOps. And I think the best example of a definition for DevOps was from my friend Donovan Brown. He also works here at Microsoft, one of our awesome DevOps folks. I've learned a ton from him, as well as his friend Abel Wang, who is a dear friend who passed away recently. DevOps is the union of people, process, and products to enable the continuous delivery of value to our end users. Now, this is the important bit, and this is super important. Value to our end user. It doesn't say, the continuous delivery of our software or the continuous delivery of our flyers or anything like that. It's value. The important thing is, how are we delivering value to our customers? Now, this is easy and I say easy, quote unquote, because it's actually hard to, but this is easier if you're just working with code. I mean, the thing compiles and it does the right thing, or it doesn't. When it comes to machine learning, the questions, the things and problems that come up are way different because there is an uncertainty that exists. Let me give you my typical flow of the machine learning process. Typically, I want to know if a thing even works. So I go to the Jupyter notebooks and I start, typing things in and figuring things out. And like, what is a convolution? Does it even do the right thing? Because I don't believe it, and I'm going to try things out. And then the next thing we have to do is we have to somehow get some data to map into the code that we're writing, right? And that process is often not fun. Because do we even have the right data? Is it labeled properly? Do we need to figure out a way to get it labeled properly? Once we do, are there mismatches? For example, are the numbers that I'm getting quarterly on one column and daily on another? Do I have to impute values? What about null? So you get the point. We're not going to talk about that part during this talk. We're going to talk about from this point on. The next thing is, once we do get our Jupyter notebook, the process for making a model is simple. Not really. We have to try a bunch of things. But again, once we get to this point, it's the fun bits. The data bits is the part that is not as fun for me. I love doing the models. And so I try a lot of stuff and the time flies by. It's because there's just a ton of happiness here. But then once we get the actual model, what happens then? Well, we have to write some code that can consume the model and then hopefully write something that makes it so that someone else can use the model without having to know. Because if you're like, hey, I want you to convert that picture to a 224 by 224 by 3 tensor. And by the way, since I'm using PiTorch, can you put the channels at the front, right? And then pass it in. No one's going to ask end users to do that. So we have to ostensibly write some code that protects us from the end user so that we can handle anything that they would send at it. Like, for example, they sent a picture with an alpha transparency. Then everything breaks, right? And what are we going to do with that? So we got to write some code, and then we got to do the endpoint. I'm going to try to use sound effects, if that's okay. And then once it's in production and we're like, we did it, everything's done, then we recognize that the data that we get for inference isn't even remotely the same or is a little bit different than the data we use to train, and so we've got to do this process all over again. This talk is all about how to prevent tomorrow's headaches today. If we can unconvolute, and I'm using it not in the like computer vision convolutions, but if we can undo this circuitous path and find a way to operationalize this stuff in a better way, we're going to save ourselves a ton of headaches moving forward. So MLOps is the same as DevOps, but more, it feels like I should say tortured, difficult, hairy, and it's because of this stuff. The data source and provenance. Data sourcing and provenance is hard. The experiments. I didn't even get into this one, but like, for example, let's just say Sally is such an awesome data scientist, and she gets hired, to run her own company for millions and millions of dollars. And then I come in there and I'm like, oh, here's the model. And I open it with Netron. And I'm like, I kind of see what she did. I wonder if I should try this. And all of a sudden, all of the wisdom that Sally created while building these models is completely gone. That's not cool. Also, there's this notion of specialized environments, sometimes specialized hardware. Then we get into the inference data, single training data, and the goal is to make it repeatable. So let me change the DevOps definition into MLOps. And I left DevOps in there on purpose because it's almost the same. But MLOps is DevOps, which is the union of people, process, and products to enable continuous delivery of value to our end users with machine learning, even with all the hairy nuance that we have in there. And I think that's important. For us, like I said before, what I want to do is I want to focus on this part right here. Everything after the notebook. All of this goodness. This is what I want to focus on, because using notebooks and experimenting, super important. Now, here is our agenda for today. We're going to talk about 4 specific tips. I don't do them all the way perfectly, but I want to just motivate them, if that's okay. I want you to see like how I did it myself and in this toy problem, and how you might have some ideas. We're going to talk about notebooks to structured, repeatable code. We're going to talk about the machine learning exhaust, or following the lines of inquiry. We're going to talk about continuous integration and deployment. And then we're going to talk about making things actually still work. Now, if I may wax poetic for a second, there is no such MLOps product. If someone is selling MLOps, that's like saying, I'm selling strength. It's almost, the thing about MLOps is it starts to become more of a culture, because it's a union of people, process, right? That people and process is the culture bit. Products is like the other leg in the stool. If you do not have unity in the people and the process, you're sitting on a one-legged stool. It's going to fall down. And so that's super important. You're going to see me using products only because I work at Microsoft and I'm familiar with Azure Machine Learning. I'm familiar with GitHub, but I'm using a bunch of different things. I'm going to use GitHub and Azure Machine Learning together to do this. I would be grateful if you used them, but the reality is you should think about the principles that we're talking about and ask yourself if you're including them yourself in what it is that you're doing. All right, so let's start with notebooks. Here's a screenshot of a notebook. Let me just open the notebooks that I have and show you what's going on. All right, so here is my code. Notice that usually you get code from the data scientist. It's in the form of notebooks, or maybe your organization is better than mine, but you get notebooks that says, here, I made the thing work, now move it to production. This happened to me once. I got some code from Microsoft Research, and they're like, hey, put this into production. And the funny thing is I could see where they changed their mind in the code. It wasn't the best code. And I know folks are notorious for saying things like, well, data scientists aren't good coders. No, that's not it at all. The reality is that data scientists are write code to prove something works. Me, machine learning engineer, am writing code to take the proved model code and make it into a repeatable process. And that's super important. So let's go to the notebooks and see what we got. Okay, so looks like data scientist Seth was learning how to figure out convolutions. He wrote his own conv2d. Good for you, son. Good for you. There's a max pooling. Look at him. He was trying to figure out what this is a pretty good thing. But again, this has nothing to do with putting this into production. Let's look at the other notebook. Data scientist Seth looks like this was his 27th iteration of this particular thing. Good job, Seth. But there are certain patterns, especially if you're doing deep learning or any type of neural networks, etc. You know, there are some things that kind of start to happen all over the place every time. For one, you've got to get code to pull data out of the original place and transform it so that it's tensors so that it can be pushed down. Now, this is also the case if you're using traditional machine learning models like scikit-learn models. You've got to convert these things into vectors or into something, or you got to do something. Now, notice that for me, I'm using transforms, data loaders, and data sets because I'm a PiTorch person. I'm a fan of PiTorch, and that's what I use. And notice that we have some data loading code right up in, you can see it just literally, I'm pointing the wrong way, right over here. You can see all the data loading code, as well as this random split. And so there's always data code. Second, the second thing is there's always this notion of the model code or the shape of the model. This really isn't the same if you're doing scikit-learn because you're just instantiating, I don't know, like you're doing a logistic regression, you just instantiate it, right? But there's still that aspect of the model itself. And then last but not least, there's always this code that I like to call the loop. And you can see the loop is right here. The loop. And notice there's also this notion of, like, for example, the loss function and the optimizer that you'll see in there. It's always in there. And whatever circuitous path the data scientist took to get there, you're going to find these elements in there. But you need to look for them. So the goal is to put this into more structured approach. And to do that, I always like to look for three things. The first is the data code, the model code, and the loop/fit. And the tip for tip number one is put that into structured code in a way that anytime you ever do any of these models, you have a sense for where things live. Now, for me, like I said, I use PiTorch, and PiTorch Lightning is a wonderful framework that puts everything in its place. So, for example, when it comes to the data, notice that I'm using a Lightning data module. And that Lightning data module has everything that it needs to know about, like for the setup, how we set up. So there's some transforms. This runs when the training starts. There's the transform. Here's the target transform. Here is the data set. Notice that you have to pass in the data to figure out where it is. And then it has a training data loader as well as a validation data loader. It's all in one place, all the data. In fact, I am so forgetful of things, and I want to remember in 20 days when I look at this code, like where it is, I literally call it data. Now, there's other frameworks that you could use, but if you could find a way to structure your to structure your code that you get from the notebook into a repeatable process, you'll know that when you get a new notebook, you look for the data code, you look for the model code, and you look for the quote-unquote loop, and then you put it into the structure that works, and you test it locally on a small data set. And once you do that, it's nice. Here's the model code. I forgot to do that. Notice that here it's basically the same code that you see over up in the notebook, right? You can see vision model. Let me split this to the right, and then let me close this. You can see pretty similar, right? There's the extra and the fully connected node here, and then I just add some more stuff, and then there's the forward, exactly the same. But with PiTorch Lightning, it does a training step and a validation step, which you saw me kind of do, the data scientist me do in the past, which is super nice. And then here it puts everything with the optimizers here, and then I added a save method to save stuff out for me. And then finally, so there's the model code. The last piece of code that we wanted to talk about is this notion of the loop. Now, what does that look like? Well, in PiTorch Lightning, there is something called a CLI method that what it basically does is it marries the model code, which is the model, and the data code together and runs them. I'm using MLflow to auto-log things so that I can make sure things are happening. And then after everything is fit, I log out some artifacts, like, for example, the Onyx model, and then some extra parameters, like how many parameters are in this model, what's the model size, and what's the model type. And I just basically load the best from Checkpoint. Now, here's the thing. Let me zoom in because I said a bunch of stuff and it was hard to see. Here's the thing. It doesn't matter what you use, only that you put it into structured code. Because by the very nature of notebooks, it's designed to be unstructured experimentation. Moving it into this structured mode will save you a lot of future hassle. And I've heard of people take notebooks and then run them in I'm not going to say production, but in a training environment, which is fine, but that becomes very brittle for people in the future. That might be my opinion, but I think it's a good one. It saves you some trouble, and it allows your engineers to know where everything is. Okay, so we have the data code, the model code, train loop, and fit. Notice that I did that. There's my data, there's my model, and there's my train code. Perfect. Tip number 2. The breadcrumb trail, machine learning exhaust, following the lines of inquiry. A little story, when I was in grad school, I was doing computational linguistics, and we were trying to figure out if we could automatically, from a bilingual corpora, be able to have it learn to match words on its own. We used something called the Hilbert-Schmidt independence criteria, and it forced me to solve a quadratic programming problem. Now, I'm only saying this because it was a colossal failure. And I spent a year rebuilding a QP solver in MATLAB and Python and whatever other language, I don't even remember. But what happened was I would go down a certain line of inquiry and would dead end. And the problem is, now I'm going to take this for granted. You should use source control. I didn't use source control. And so I would follow this line of inquiry. And all of a sudden, I'd be like, dead end. And I'm like, well, I need to go back a few steps. How do I even do that? So this is where products help. The reality is you need to find a way to log everything out so that if you were to go at it with fresh eyes, you would be able to pick it up. Or if, say, when Sally left, because she did this and she's the best data scientist in the universe, and I go back, I need to be able to reliably figure out what happened and what were the lines of inquiry. Detailed notes. This is the science part of data science. So the question is, how does one do this? And this is where I'm going to show the tools that I'm used to, Azure Machine Learning. So let me go to Azure Machine Learning here. I think I can stop. No, I'll just leave this on. It's okay. It's okay. I'm going to go to Azure Machine Learning, and what I'm going to do is I'm going to refresh. Well, let me go to the experiment. And you're going to see that there is something that ran just now. Now, you're looking at this in the future, but this happened, 20 minutes ago. So let's go over to it and let's look at the kinds of things that you should log. The first is, what did you use to run this experiment? And I'm going to zoom in here so you can see. Notice that I know everything about this thing. I know the learning rate. I know that it was using monitor. It was monitoring the validation loss, so it didn't have to go to 100 epochs with a patience of 5. I know that it needs a min delta of this. I know the model size. I know the optimizer name. I know basically everything I need to know about the parameters that went in. The second thing I know is I know the exact environment that it ran in. And this is the thing. I mean, we can't have this. It ran on my machine business. So if I go to the PiTorch Lightning environment, you'll see that I can take a look at the exact Conda environment where all of this ran, and also that it ran using CUDA Toolkit on a GPU. Great. Let's go back. The next thing is I can take a look at all of the metrics. Now, obviously, this is a toy problem and all the curves look beautiful, but it might not be the case that all the curves look this beautiful, and that's okay. I know that it stopped at epoch 20. I know that it got to good accuracy pretty quickly, and the loss continued to go down on the training, and same for the validation. Looks like the top accuracy was 99%. The next thing I know is, and this is super important, is that anything I printed out is stored here as well. Now, again, use whatever you want, but leave a breadcrumb trail. I promise you, this will save a lot of headache in the future, and your future self will look at your past self and say, "Self, thank you. You're welcome." Seriously, because I know even down to what I was spitting out, what was going on. You can see the last loss was 0.00844. But it also spit out like the MLflow model, which is nice. I didn't have to do that. I was using auto logging for MLflow. By the way, auto logging for MLflow is what makes all of these things come out here. Because MLflow is awesome. You should use it. I know I do. That's where these charts came from too. I'm sorry. That's where these charts came from too. Because MLflow just logs everything with PiTorch Lightning. Okay. And then there's the specialized model that I built with the metadata that I can use to, use the model, score it, or do inference. Okay. So there's the details, there's the metrics, there's the actual logs, as well as everything that was spit out. It's all in there. Glorious. There's no need to even wonder what's going on. And not only that, but the other thing that's important to recognize is that you have all of the charts of everything that's going on for all of the experiments. Now, you're looking at this and you're like, wait, Seth, that's a lot of runs. Yes. Yes, it is. And I'm okay with that because I've done a lot of experiments, right? And you can see them all in here. Okay, so that's tip number 2. And tip number 2 was about showing you the way to leave a breadcrumb trail for yourself. Again, these are in the slides. I want to leave them in there so you could see them. Okay, tip number 3, continuous integration and deployment. You need to allow yourself some space to make mistakes. That's what this whole thing is all about. Now, that sounds weird. It's like we need to get this perfectly. But the reality is that machine learning is such a squishy thing, at least for me, that you need to allow yourself room to make mistakes. You know, that model that you saw in deployment was not very good. But I made a change, and hopefully that helped. So let's go over to this other tool called GitHub, and let me show you what I'm doing to do continuous integration and delivery. So I'm going to go ahead and click on GitHub Actions and show you that this workflow run was the trying a ResNet 18 run that I literally checked in just a minute ago. You remember, I checked it in and I said trying a ResNet 18 because the other one just was not working all the way. Let me show you the steps that it took in order to get this to work. Let me make this just a tiny bit bigger. There you go. Notice that, again, and this is the important bit, these are the steps that I took to make sure that this thing was built and deployed. Your steps might look completely different because of the way your infrastructure is set up, or the way that your people are set up, or the way that your process is set up, because it's the union of people, process, and products. The product I'm using here is GitHub. You can use other things too. It's just I like GitHub and I like GitHub Actions. So the first thing that I wanted to do is I wanted to make sure that there was an endpoint set up, and that's an Azure machine learning ism. That might not be a step that you need. So I checked to see if the endpoint is made, and if it is, great, then deploy, but only deploy as soon as you register and run the experiment. So let's talk about running the actual experiment. So GitHub here is tied into Azure Machine Learning. And so it basically, you can see I basically run a command that says, create a job with this description, with this description. And then it names it, app name, GitHub run ID. So that it runs it. And then it uploads it, and because I do -- stream, it just spits everything out. And you remember, hopefully early on, I showed you the last loss value. And you can see that last loss value is indeed 0.00844. And let's go over here, because it's literally just mirroring. It's mirroring the output of this. It's not like running it on GitHub, because there's no GPU. I don't have a GPU machine to run on GitHub, and so I just tell Azure Machine Learning to do it. And if you have a question, there's a ton of things that I'm alighting. I'm just looking at the 4 principles. Feel free to reach out to me, because I want to make sure you get that. You can see it's 0.0844. It's exactly the same thing that we just ran. Okay, very good. Once we run the experiment, there are the artifacts that I showed you in the output folder. I need to register those. What does registering a model mean? Well, I mean, if you're looking at MLflow, there's a model registry there. You just basically need to save the artifacts that are useful for running the model in production. For us, that's basically putting it in this model registry. And you can see this is the 34th model that I've run. I should probably add more stuff in here, like the framework version, experiment name, etc., or tags. I didn't, because I was in a hurry, but don't tell anybody. But here's another reality. It took me 30 to 34 times to get this MLOps process working smoothly, the way I wanted it to. And that's okay. This stuff is hard, and it takes a while to get it set up properly. And that's quite all right. Not a problem. It's not anything to be ashamed of at all. But once it's set up, it's glorious, because I made a mistake, I made a change in code, and now this thing is going out, in this process. Okay, so let's go back to the summary here. That's the register, the model part, and there's this thing called deployment. Now, the thing about this that's tricky is you've got to find a way to put this out so that people can test it, and in a safe way so that customers aren't impacted. Because again, the goal is to deliver value to customers, not negative impact. So for example, another smart way of doing this might be to have a release gate that tests it on some of the Rochambeau images that need to work in order for this to go out to production. And then if it doesn't, just fail it. And that's okay. I didn't do that. I just release them all to production, which is maybe not a good thing. But notice that you can do other steps. And hopefully the principle is starting to make a little more sense. And I mean, I'm sure some of you, I'm like telling you stuff that you kind of already inherently know. But notice that it's not so important what the process is, but that the process is repeatable. And that's what it is for me now. Okay. The deployment for us is, let me go over here to the add deployment. And notice that it basically uploads a deployment and routes some traffic to a deployment. And that's awesome. So let's go over to what that looks like inside of Azure Machine Learning. It may look different inside of whatever it is that you're doing. Let me go over here and notice that the production deployment of this thing is build 138661 blah, blah, blah. And that's the one that has 90% traffic. What happened was, and let me go to the GitHub action to show you what's going on. What happened was, let me go to GitHub training. When it does the add deployment, it checks for the prod deployment. And if there isn't one, it knows that it needs to deploy one of them. But if there is one already, notice what it does is it creates a new endpoint and then maps traffic to it. So that I'm not just like replacing the thing that we know works, I'm adding a new deployment and routing traffic to it. And that's a way to do it safely, right? So I guess it's time to test this. So let's go over to the test area here. 13866 was the model, I think was the older model. Let me go back here. So we want 13869, which is the new model. So let's test it. 13869 is the new model, and let's test it, see if it works. Yes. So this one's a little better. Okay. And this brings us to the other bit of code that I talked about briefly, but I'll show it to you now. So I have a scoring file right here that shows how I actually score things. And this will run locally as well as in the cloud, and that's the important bit. And there's two methods that are important. The first is the init method, and the second is the run method. The init method initializes the service, and the run method runs it. Now, this is wrapped in a Flask application that then is deployed on Azure on its own. But I just need to write these two methods with my scheme, the way I do it with Azure. Now, the thing is, you can do this any other way that you want, but make sure that you have specific places where you initialize and run the thing. So notice in this case, model loading looks at environment variables to know whether it's running inside of a cloud context or not. So this will actually run locally or wherever you want. The second thing is this little ditty that looks confusing, but it's not. It's basically saying this is the format of the thing I want in, and this is the format of the thing that's going to come out. The reason why this is useful is because then you can do Swagger documents so people know the shape of your API. Because you're not going to say, hey, user, I want to make sure that when you pass things in, it's a three-dimensional tensor of size 224 by 224 by 3 channels. Put the channels in front because PiTorch decided that's the way it's doing it, and then normalize and then send it. Otherwise, we're not. No, nobody wants that. The other thing is you need to make sure to check if it's going to break, because you don't want to break things. So one day someone's going to send a PNG that has an alpha channel and everything's hosed. No, you got to be clever about how all of that stuff works and send errors if things do not work. Okay. So there is the test. For that, looks like it is indeed working. Let's go to the details, and let's update the traffic, because moving this thing into production is something that I want to do manually. So I'll update the traffic, and what we're going to do is we're going to test it out on our new deployment. So it looks like our new deployment is this one right here. So I'm going to take this and this, and you're probably wondering, well, why are you doing this manually? Well, because for me, that's the process. Production changes need to be manual. I guess. I mean, I guess that's the rule we're doing. So you can see 100% now is over there. Now let's go to our stylish demo. Still running. Wow. Now it's a little better. Let's put a rock there. Ooh, scissors. Paper. Here, let me do paper here. Yes. Scissors. Yes. Rock. Oh, it still thinks it's scissors. What if I get it closer? Okay. So looks like it's a little bit better, but also notice that the model timestamp is different than the one it was before. And by the way, this was running the whole time. Oops. Okay. All right. So that was the continuous integration and deployment. And now in the last couple of minutes, let's talk about the final bit. So you saw this. Making sure things still work. Do our models age well? All right, let's go back to, I stopped that. Fantastic. Let me close this because memory. Let's go back to this endpoint and let's talk about this notion of understanding what is going on. One of the things that I did not show you is in the scoring file, we have a ton of print statements. I probably should have used logging, but I didn't. Sorry. But with these print statements, I'm able to actually look at these things running inside of production. Right? There's the payload. Notice that it was happening every second, and you can see all of that in there. But notice that I actually output a lot of stuff. I should have output a lot more. Like, for example, I should be saving these images. We should be doing some QA in the background to figure out if the data that's coming in is the same kind of data we used to train. And then when you find a huge difference, retrain. And that's the part about keeping this thing and delivering value continuously. Now, here's the thing about this. This is nice, but let me show you an even better way to do it for me. So we'll go to the Azure portal. And what I'm going to do is I'm going to go ahead and go to the back end or the thing that I use to run. This is called my Azure Machine Learning Workspace. This is what I called it. These are the jokes, people. These are the jokes. Let me go over to HAL and let me show you this application insights tool that allows me to look at these logs in a better way. By the way, you can see all of a sudden you're starting to get all the server requests. There were a ton because I was doing them every 3 seconds. You can see the response time was actually kind of high and then it went down. Oh, so it looks like that deployment change did a good thing for us. You can see the server requests went down a little bit. You can see the availability. Awesome. Let's go over no failed requests. Thank goodness. Let's go over to the logs. And let me run this particular trace so I can see all of the payload. So this is every single call that was made to these things. And you can see inside of it, I have the custom dimensions that show the payload of everything that we did. If I was smart, I would also output the pictures to some kind of storage, map it to this, so that then I could create a situation where I can get more data and to figure out if the assumptions we made at training time actually work at inference time. All right. So making sure still work. Did our model age well? Are we logging and saving these things out? And that's what we should be doing to know if the data that we used is the same data that we use. The data we're getting is the same data that we used for training. All right, so I used this thing as a crude first approximation, and then I used this to do a better approximation. And again, there's probably a lot more I could have done with saving the actual images, but I didn't. All right, so let's review in the final minutes. Notice that the thing still didn't work all the way, but that's okay because I can do more experiments in the notebook. I can figure out how things actually work a little bit better with the data. And because I've chosen a framework or I've written one to manage the data, the model, and the loop, once I'm done with the notebook, I know exactly which code to pull out and where to put it. And then I just check it in. As I check it in, and the thing runs. Tip number 2 was I found a way to document every machine learning experiment so I can view everything related to the experiment. The other thing that I did not mention is hopefully you use source control, but if you don't, for us, when we do these things, we save a snapshot of the exact code that you use to run this experiment. All of it. All of it. So you have everything at your disposal when you're actually looking at the breadcrumb trail so that you can figure out later on, if you get to a dead end, how to go back. That was tip number 2. Tip number 3, use an automated process to build and deploy models. I used GitHub Actions as well as Azure Machine Learning as a model registry to deploy the model to production safely with slots. Now you got to do it. The way that you do it is awesome, I'm sure, but just make sure you do it safely and you have an automated way so that you can make mistakes quickly and you can figure out if it works quickly as well. And the last thing we looked at is making sure things still work. We need to log save data to measure drift. We need to log and make sure that the application is doing well. Like if all of a sudden, the request time goes up, maybe there's something wrong with the hardware. And notice that throughout all of this, the notion of environments sort of kind of burned in to everything we do.